So now I'm gonna start talking about the Weil-Petersson Teichmüller space. And I'm going to abbreviate Weil-Petersson as WP all the way through. It'll save a lot of time. And I'm going to shamelessly plug our survey article. Wolf Staubach and I wrote a survey article called Weil-Petersson Teichmüller Theory of Surfaces of Infinite Conformal Type, something like that. And it has a complete history with, not a complete, but as much history as we could pack into the chapter. So it's a book chapter appearing in a Springer volume in the tradition of Thurston. So I'm also doing that out of a sense of responsibility. So the actually getting the citations right is quite hard. There's a lot of people who've worked on this. So there we made a big effort to give credit as much as possible, to everyone involved. Okay, so now, so there's this Weil-Petersson pairing. So, and it originated in finite dimensions where it works. So this is an L2 pairing on the tangent space. And essentially, if you have two quadratic differentials, one of the descriptions of the tangent spaces as quadratic differentials, you weight properly with the hyperbolic metric. Actually, I should have used the hyperbolic metric here. Lambda to the -2 over the surface. Okay, maybe it's a little easier if I write it in terms of the, oh no. Okay. If I write it in terms.
Probably talking over there.
Yeah, okay. Maybe I'll write it on the disk here. F is a fundamental domain of the disk. It's a fundamental domain on the disk. So if you, or in the disk, I should say. So you cover by the disk, and then you choose a fundamental domain, which is so that you act your Fuchsian group on the fundamental domain. You tile out the disk, and you weight the quadratic differentials by the hyperbolic metric. And this is a pairing on the tangent space. This is just some history for a minute. So I'm being very loose for the moment, and I'll be more precise after I'm done with the history. So, and this is generally said to be due to Petersson and Weil. I should actually probably say Petersson and Weil instead of Weil-Petersson, but somehow this ordering has stuck. So, Petersson first considered in 49 in association with modular forms, with both including cusps, and they returned to it in 57, 58. And I believe he even conjectured that you get a Kähler structure with respect to this pairing. I can't remember exactly at the moment. So you have a pairing on modular forms. And then Alforsch showed this was Kähler. I showed that the Teichmüller space is a Kähler manifold with respect to this pairing, with respect to the inner product that you get from this pairing. So this is for compact surfaces. With respect to the Petersson inner product. And then later, there was some, this thing just simply doesn't converge on the Teichmüller spaces of infinite type. It just doesn't converge. That's all there is to it. So it's not well defined on the all-force-burst Teichmüller space that I've been talking about for the last while. And I think Nogin-Brzezinski sort of became interested in which directions somehow, or what subspace of the Teichmüller space does this converge on? Let me just write that down.
Can you give a simple reason why it doesn't converge?
That's because this is an inner product on, there's two answers. One is, if you write down what this is, a non-answer is that this thing, if it has an inner product and is a Kähler manifold, then that's a Hilbert manifold, and these Teichmüller spaces are Banach manifolds. That's kind of a non-answer, but another thing you can do is, say you take the universal Teichmüller space, and you simply write out in a power series what this inner product is, and you get some expression which involves n cubed minus n, where n is the coefficient. It's something like n cubed minus n times mod a n squared, and you just observe that doesn't converge. And that's exactly what Nogin-Brzezinski did. So this was in 1990. Oh, I gotta put a 19 into that. Fine. Or maybe not, okay. So it actually converges on H3 halves. Actually, if you 3 half order Sobolev space, if you express it in terms of the coefficients, the n cubed means you have to have a 3 halves there. Okay, and then the Weil-Petersson universal Teichmüller space. So somehow, they observed that diffeomorphisms are Weil-Petersson, not what Brzezinski did, but said that the completion is not going to satisfy this, that if you try to complete quasi-symmetries, it doesn't work. But then you can ask, what's the biggest space you can complete to? And that was started by Hui. And I can't remember, I think they don't actually reference Nogin-Brzezinski. They're sort of independently thinking of what happens if we put an L2 structure instead of an L infinity structure on the space. So this started with Guizhen Hui in 2000, and then Guo Hui also in 2000. They actually considered LP Teichmüller spaces, and not just L2. And then a lot of people know about this Taktajan and Chio monograph, which came out on the archive in 03 and 04. It sort of came up with a pretty, there's a very complete theory. When you put all those together, there's a very complete theory of the Weil-Petersson Teichmüller space in the case of the disk. Okay, any questions about that history before I start making some definitions? Okay, so let me start with, I'm going to talk about the AP universal Teichmüller space. So just a warning, I'm really going to try to, I want this talk to be coherent, so I'm not respecting anyone's notation. I'm trying to pick a notation that is consistent throughout the whole talk, but we can make translations in every case with a little bit of work. There's also conventions one has to deal with. Everyone has a different convention. It's a bit aggravating, but I will. The theorems are invariant under change of notation. So, actually, I don't quite have room for the definition. Let's start back here. Also, people define the space in different ways and then show that the different definitions are equivalent. So I'm just choosing one to start with, and the equivalences follow from various people's theorems. So, the universal Teichmüller space of the outside of the disk, this is a set of Weil-Petersson quasi-conformal mappings of the disk modulo an equivalence relation. And oops, I got ahead of myself. Jeez. I'll stop. Where? I want to do it in a different order. Where QCWP D minus to D minus is a set of quasi-conformal maps from D minus to D minus, such that the Beltrami differential is in L2 with respect to the hyperbolic metric. And you may wonder what I mean by L2 with respect to the hyperbolic metric. Actually, if you don't know the definition and you just think about the weight, how this Beltrami differential transforms, you can pretty much work out what it has to be. But let me write it down in any case. So this is the set of Beltrami differentials, or sorry, negative 1, 1 differentials, which satisfy that the double integral over the disk of mod mu squared over 1 minus mod z squared with respect to this L2 integral converges. So this is a hyperbolically weighted L2 integral. And it's necessary to put this in if you want to think about how this works on a Riemann surface or make sure that it's in invariant quantity. So if we define also so let me just say what the equivalence relation is. That's the same one that I've been using all along, but I just want to repeat it. So we have F1 from D minus to D minus is equivalent to F2 from D minus to D minus. If and only if there exists a sigma, which is conformal. So in particular, it's a Mobius transformation such that F2 inverse of sigma of F1 is homotopic to the identity around boundary. And this is if and only if F2 is equal to sigma of F1 for sigma in, which is a Mobius transformation preserving the circle. Someone asked a question, do people use this notation? I'm just going to say preserving the outside of the disk. Okay, any questions about this definition? And then we can see that there's a couple of equivalent models now. So if we define also the Weil-Petersson quasi-symmetries to be those quasi-symmetries such that there exists a quasi-conformal extension which restricts to the quasi-symmetry on the boundary. So if there's a quasi-conformal extension with L2 Beltrami differential, we call that a Weil-Petersson class quasi-symmetries. And actually, another plug for Chris Bishop's paper with various characterization of Weil-Petersson quasi-symmetries and Weil-Petersson quasi-disks. I forget the title. It has the word data numbers in it, but I think it's been on his website for a long time, and it's going into annals now, I think. So that's a must if you're interested in this subject. So now let me say. Then we have several models here, so we can say, aside from this one, we can also write that the Weil-Petersson moduli space of the disk is the quasi-symmetries mod the Mobius transformations. And you can also say that it can be regarded as the intersection of the Beltrami differentials, which are both L2 and L1. But you'll still have to mod out by the Teichmüller equivalence relation on that intersection. Okay. Any questions about that? So let me tell you in a nutshell what's happening. We're replacing L infinity structures with L2 structures. And sort of a bunch of people systematically started to do that. And the advantage is that now you have a Hilbert manifold, you have a Kähler structure, you have all kinds of things like that. So, okay. Now, let me just say a couple of results here. So we have the Burrs embedding. So now if we define A22 B plus, this is the set of quadratic differentials. Which satisfy the following L2 condition. Oops, I'm saying D plus, I haven't used that here. Just mean disk. So you look at, instead of looking at quadratic differentials which have this finite L infinity norm, they have this finite L2 norm. And then you take the ordinary Burt's embedding and you apply it to elements of this smaller space, and it turns out they not only will be in A2 infinity, so they satisfy this L infinity bound, they also satisfy this L2 bound. So I'll just recall it. Remember, beta of a deformation, E minus F D minus, was the Schwartzian of F hat restricted to D in general, where here mu of, so this F was extended to the sphere in a sense by setting the Beltrami differential to be 0 outside or in the disk, and left it alone to be the same as F in the original set. So this is mu of F on B minus and 0 on B. This is the so-called burst trick. So then this F hat is conformal on the disk. So you have a well-defined Schwartzian, and the Schwartzian lands in this L infinity space. But we have the following theorem, which is by Cui and Hausdorff and Tio. Which says that P is in the Weil-Petersson Teichmüller space if and only if beta of P is in A22 of D. And here the assumption is assuming P is in the original Teichmüller space. So you get this really nice description in terms of the Burst embedding of this smaller space. And the corollary is that the Weil-Petersson Teichmüller space is a complex Hilbert manifold. So this gives a very satisfying description of this space. Also, you'll recognize that this is the pairing that I talked about earlier, and so this is, of course, precisely the space on which this pairing converges, the original one I used in the historical motivation. So, and then there's just a couple more theorems here. So there's a nice theorem of Cui in that same sort of seminal paper, the one which started the whole business in some sense, that if you define the Burst embedding to just be the restriction of the Weil-Petersson Burst embedding to be the restriction of the Burst embedding to the Weil-Petersson Teichmüller space, this is holomorphic with respect to the norm mu infinity plus mu 2. So this gives a nice structure on the space, and actually it has a global section. And then, so that's a nice result. And then another nice result of Takhtajan and Tio, if you're interested in, I mean, there's got to be some representation theorem involved if we're going to try to connect this to CFT or just, you know, generally thinking about representation of these parametrizations. Well, you know, if you want to do geometry and algebra, you need an analytic setting that makes it possible. So here's a theorem that indicates that this is a nice setting for this to be possible. Takhtajan and Tio showed that the Weil-Petersson Teichmüller space is a topological group. So in this model, this is a set of quasi-symmetries. You can compose them, that's a group structure. And with respect to the Weil-Petersson complex structure, this is a topological group. And this is not true for the full Teichmüller space. It turns out that left composition is not continuous in the Teichmüller space. That's proven in Lehto's book, but Lehto says the argument is due to Tupia. So there's some indication that this is somehow a better space for this. And there's a little bit more. I'm a bit challenged to finish this somehow. I think I can do it. Okay, and now we also have another theorem. So I'm just, again, you can talk to Jean Nikio and 3 on the archive, but this is a Kähler manifold. In fact, it's Kähler-Einstein. And then we also have the tangent space model that I mentioned. So it's also, there's an equivalent Hilbert manifold structure. Locally modeled. On H minus 1, 1 of D minus. And this is a set of 1 minus mod z squared squared B of z, such that B is an A2, 2 of D minus. So you can use this as a model of the tangent space. And if you have a tangent space, you can locally exponentiate it to get coordinates on the manifold itself. This is kind of a long story. It didn't fit into the talk. You have to go through a long story with either Weil reflection to get these local sections, and it's a bit of a long story. But roughly speaking, these are the models of the tangent space. So again, you just replace what I said in the first part of the talk. You replace it now with an L2 condition, and then you have a new model. Okay, I'm doing okay for time. Let's see. Any questions up to here? I'm now done the universal case, and I want to move on to the general case. Okay, all right, so now I want to talk about Weil-Petersson Teichmüller space and Segal moduli space for genus G with n orders homeomorphic to S1. So let's start with the definition. So I want to define a Weil-Petersson class quasi-symmetry. So let's say we have two Riemann surfaces. They don't have to be of the same type, but I will be considering them to be of the same type in general. So you fix one boundary curve on each of the surfaces, and you say, if you have a parametrization, or if you have a map between the two, there's a Weil-Petersson quasi-symmetry. If in some sense it's a Weil-Petersson quasi-symmetry in local coordinates, so you take, I think I used yellow for this. So take a coordinate here and a coordinate here, map it down into an annular region, and I'm going to take this as now S1. And your phi goes like this. Call this C1, and call this over here, call this C2. And you say C2 of phi of C1 inverse is a quasi-symmetry of the circle. And then using the Schwartz reflection argument, Kerr-Theodore's theorem, you can show that this is independent of the choice of these charts. So you have a well-defined notion of quasi-symmetry of the boundary curves. So that allows you to make the following definition. When was this? This was. So you say that the Weil-Petersson Teichmüller space for genus G with n borders this is the set of quasi-conformal deformations or the set of elements of Teichmüller space specifically that such that F restricted to each boundary curve is a Weil-Petersson class quasi-symmetry. So you determine the Weil-Petersson Teichmüller space by demanding that the boundary deformations are Weil-Petersson quasi-symmetries. It's sort of a natural extension of one of the models in the universal case, but it's somehow in the spirit of the Segal moduli space. So, and so, I mean, this definition can sort of fit almost immediately into the Segal picture. You know, I'm going to write it down, but essentially, you just replace the quasi-symmetric or smooth parametrizations in the Segal moduli space by Weil-Petersson quasi-symmetries, and then you have Weil-Petersson Segal moduli space. we can also define Weil-Petersson Segal moduli space. So essentially, you say that I got too many superscripts, but they're all necessary, unfortunately. So you look at the Segal moduli space, where you have a Riemann surface and boundary parametrizations, but now you demand that that phi consists of boundary parametrizations, which are Weil-Petersson. So we also define the rig moduli space in this setting. I'm labeling the definitions because different people gave different definitions, and the equivalence is not entirely trivial, just as it's not entirely trivial in the classical case. So there are things to work out, so I just want to label them. Okay, and now in the puncture model, we need to talk about what are the OQCR. So I want to talk about in the puncture model you have these non-overlapping mappings, so I need to add a condition to just quasi-conformally extendable. So this is a set of mappings Fn such that F, let's call this, so F is in OQCR, and I have the following. So this and is a bit long, so I'll put it outside the brackets. So you have that the pre-Schwarzian is in A1, 2 D for all K. Let me draw the picture again. You take the you take some local coordinates surrounding the rigging. And you get a well-defined map from the plane into the plane, and now you can look at its pre-Schwarzian, and you demand that the pre-Schwarzian be in this L2 space. You could also give an equivalent condition on the Schwarzian if you like. The Schwarzian has to be an L2 quadratic differential. So then, MP as you might guess now, this is the set of R, F, mod the equivalence relation such that R is punctured and F is in OQC WP of R. Okay, any questions about that? Okay. time. Okay, there's also an alternate definition. Which goes like this. So so let sigma be genus G with n borders. Then sigma f sigma 1 is in the Weil-Petersson Teichmüller space if and only if there exists a sigma f tilde sigma 1 in the equivalence class such that the Beltrami differential is L2. And so that gives you an equivalent definition. We can just replace with those with quasi-conformal maps whose Beltrami differential is in L2. So then we get this equivalent definition that we look at the space of quasi-conformal deformations where the Beltrami differential is in L2. Okay. Any questions about that? Okay. I'm going to try to give a short version of the remainder because it's been a long haul, so I want to try to let's see if I can do it. So we have the complex structures. So initially what happened is, because David Wolf and I, we decided that, that we really needed to have this Weil-Petersson Teichmüller space with some of the basic theorems, and we wanted to construct a complex structure. And what we did is actually use the fiber picture to construct the complex structure in the Weil-Petersson case. So we built it up from the fiber structure. So OQCR is a Hilbert manifold locally modeled on these Banach, on these Hilbert spaces of one forms. And this is David Wolf and I. And as a consequence, we could get a complex structure on all the spaces. I'll try to give the short version. So we have PWP sigma. There's a Hilbert manifold. Of course, put everything in here at once. And then we get this Weil-Petersson rigged Segal moduli space. And so this gives us the fiber structure. So this is complex structure number one, I guess. And then we can also model the tangent. I showed that it was equivalent with the tangent space model. So David Wolf and I. RSS is always David Radnell, Wolf Staubach, and I. And actually, I've been doing that with Taktjajan and Thiel because I refer to them so much. T and T is always Taktjajan and Thiel. Let's see. This is compatible. I'm giving short versions of the theorems now. So the complex structures, number one, is compatible with the tangent space structure. Given by these harmonic Beltrami differentials. So then that's the second complex structure. So the main thing is I want to get all the complex structures that have been established now, and I really need to do that, I think I just have a little bit more to say. Let me just stop here though. Is there any questions? Okay.
I was just thinking to say what you want to say. Okay.
Yeah. Right. And so then there's a nice couple of papers by Yanagishida, which then give another definition, another very natural definition of the Weil-Petersson Teichmüller space. And so if you say that G be a torsion-free Tikutsian group, then you say that the Weil-Petersson Teichmüller space, you can model it by the G invariant Beltrami differentials. say it like this. So if you remember from last time, you can demand that the Beltrami differentials are G invariant, and then you get a description on the lifted disk, on the lift to the disk. And notice this is, now this definition is in greater generality. So this includes in particular the definition I was giving before for genus G surfaces with n boundary curves. And I just want to say that it agrees with the earlier definition. Restricted to type Gn. So actually, let me just give, I really want to list a few of these theorems. So, okay. So, I'll put them in one here. So beta of the Weil-Petersson Teichmüller space is a subset of the beta of the usual Teichmüller space intersect with the L2 Schwarzian, or the L2 quadratic differentials. And actually, beta is a homeomorphism or beta restricted to TWP is a homeomorphism onto its image with respect to a natural distance. It's almost like Teichmüller distance. You have to tweak it a little bit but I just want to say it's the natural analog of Teichmüller distance. I'd like to say, but I think I'm pushing it. And so now this is the third complex structure. This is the verse embedding. So just a couple of things I want to mention. He had to add here if he satisfies what he calls Lehner's condition. And that's a condition, it's a lower bound on the length of the geodesics in the Riemann surface. And it includes our case that we were considering about 10 minutes ago. So again, this actually restricts to the case that to the case of genus G surfaces with n borders. So he also showed in a later paper that if t equals 2, So this is again Yonagishita in 17. Just have to give the short version. This agrees with the tangent-based structure. In a lifted picture. So now this is, so now, once we have that, all three of the complex structures agree. Once we have that, which is very nice. I also want to mention that he showed that this is scalar. If G satisfies this Laner's condition. So in other words, the theory is pretty well developed now, and it can be used. It's now ready to be used for all kinds of things. Okay, I think I better stop here. Sorry for going a little over.